The preservation of a military aircraft underwater is usually dictated by the violence of its crash and the chemistry of its environment. When salvage crews began a 1994 recovery operation in Lake Michigan, their target was a United States Navy Douglas SBD-5 Dauntless, designated Bureau number 36175. The objective was the retrieval of a highly intact airframe for long-term preservation within a museum collection. The stakes of this operation were defined by a procedural failure that occurred nearly 50 years earlier. This was not a combat loss. It was a failure of geometry and energy management during carrier qualification training. To understand why this specific Dauntless ended up on the lakebed, one must look at the mechanical and logistical constraints of naval aviator training during the Second World War. The airframe was officially accepted into Navy service on October 4, 1943. Instead of receiving a frontline combat assignment in the Pacific Theater, this SBD-5 was diverted to a specialized domestic mission. The Navy required a massive influx of pilots capable of executing precise carrier landings. To achieve this without pulling critical fleet carriers away from combat zones, the military established a unique training environment on the Great Lakes. The centerpiece of this program was the USS Wolverine. This was not a purpose-built warship. The Wolverine was a converted civilian paddle wheel steamer, heavily modified to feature a wooden flight deck. Operating a training carrier profile on an inland lake introduced severe operational constraints. A fleet carrier at sea can turn into strong winds and steam fast, building a powerful headwind over the deck that lowers an aircraft's relative speed on approach. Wolverine couldn't generate that same cushion on sheltered Lake Michigan, leaving students almost no margin for airspeed or glide path. Landing an SBD Dauntless on the Wolverine required absolute precision in airspeed and altitude control. The SBD Dauntless was designed as a rugged dive bomber. It featured a heavily reinforced aluminum semi-monocoque fuselage, robust wing roots built to withstand the extreme stress of dive pullouts, and heavy steel engine mounts built to carry the shock and vibration of a radial power plant, while arresting loads on a carrier deck are taken through the tail hook and the aft structure. Flying this heavy machine at the absolute minimum controllable airspeed required significant skill. At low speeds, the control surfaces become sluggish, and the radial engine must carry more of the aircraft weight to maintain altitude. The landing signals officer serves as the ultimate safety authority during carrier recoveries. This officer continuously evaluates the approach geometry, descent rate, and airspeed of the incoming aircraft. If the parameters fall outside the safe operational envelope, the officer executes an aborted landing procedure known as a wave-off. This is a mandatory command requiring the pilot to immediately apply full engine power, or arrest the descent and clear the deck to attempt another circuit. The decision logic is binary. Either the approach is safe to trap, or it requires an immediate wave-off to prevent a deck collision. On the cold winter day of January 20th, 1944, Bureau number 36175 was actively engaged in these carrier qualification circuits. As the pilot turned onto the final approach leg, the geometry of the descent began to break down. The officer observed the Dauntless developing an unsafe energy state, sinking and bleeding speed. Accounts vary on the exact trigger for the wave-off, but the approach geometry was clearly trending outside the safe envelope. He first signaled "come on" with his paddles, directing the pilot to add power and correct the approach. In the cockpit, the response was either too slow or too small. The heavy dive bomber continued to sink toward the stern of the ship, its energy state now critically low. The officer reached the irreversible threshold of his decision logic. He crossed his paddles, wave off, demanding full power, wings level, and an immediate climb away. The officer had correctly calculated the decaying energy state and issued the only safe directive. How does a strictly procedural wave, off command, escalate into a total airframe loss in a matter of seconds? A steep bank angle combined with low engine torque creates an unforgiving geometry limit for any heavy aircraft flying on the edge of a stall. When the landing signals officer commanded the mandatory aborted landing procedure, for the pilot of the SBD-5 had fractions of a second to transition the machine from a descending state into a climbing turn. To clear the flight deck of the training carrier, the pilot instinctively initiated a sharp bank away from the ship. However, executing this evasive maneuver required a massive and immediate influx of thrust from the heavy radial engine to sustain flight. A radial piston engine can respond sluggishly when the throttle is slammed forward at low speed and high drag, and the propeller governor must catch up before full thrust is available. The pilot aggressively applied the throttle, but the delayed power delivery was fundamentally insufficient to counteract the sudden, massive increase in aerodynamic drag generated by the steep bank angle. This severe mismatch between commanded geometry and available engine power triggered an immediate aerodynamic lift failure. When an aircraft is pitched or banked aggressively at a low airspeed, the smooth airflow traveling over the top of the wings detaches from the aluminum skin. This separation instantly destroys the lifting capability of the wing, converting forward-flying momentum into an unrecoverable vertical descent. For Bureau number 36175, the loss of lift was entirely asymmetric. The low wing stalled first, violently rolling the heavy dive bomber onto its back as it fell toward the surface of the lake. There was no altitude left to trade for airspeed. The Dauntless impacted the freezing water in a near vertical, inverted attitude. At high velocity and a steep attitude, the surface of a lake can hit like something far harder than most people expect. Water barely compresses, and the impact loads rise brutally fast as the airframe tries to force that fluid out of the way. This physical reality meant the entire kinetic energy of the falling aircraft had to be absorbed directly by the rigid aluminum airframe in a fraction of a second. This sudden arrestment of forward motion initiated an extreme impact load separation. When a high-mass aircraft strikes an unyielding surface, the violent deceleration force is focused instantly on the forward structural joints. The engine mounts were built to handle the horizontal strain of a carrier deck arrestment wire, not a vertical crushing force against an incompressible fluid. Because this dynamic load vastly exceeded the engineered sheer strength of the heavy steel mounting bolts, the engine was cleanly torn away from the primary structure. The physics tore the radial engine free in a single instant, ripping through the cowling and snapping fuel and hydraulic lines. Modern forensic site documentation would later map the precise violence of this geometric failure. Surveyors located the detached engine resting on the mud roughly 80 feet away from the main fuselage. That separation pattern is a lasting clue to the violence and general direction of the breakup, even if it cannot, by itself, pin down an exact heading or speed at the moment of water entry. Despite the catastrophic structural failure of the forward section, the localized crushing of the nose absorbed a significant portion of the lethal kinetic energy. This structural sacrifice left the cockpit section relatively intact. The pilot survived the violent water entry with deep cuts to his forehead and other injuries, and the separation of major components may have reduced some of the crushing loads that reached the cockpit. The heavily compromised airframe bobbed briefly on the surface of the lake. This short flotation window granted the pilot just enough time to unbuckle his harness, open the canopy, and escape into the freezing water before the residual buoyancy was entirely lost. The heavy engine, already torn loose, sank first, dropping straight to the lakebed. As water violently flooded the shattered wing roots and the open forward firewall, the lighter fuselage slipped beneath the surface. It descended through the dark water column until it struck the muddy bottom, settling completely upright. How does shattered aluminum survive uncorroded at the bottom of a lake for half a century? 177 feet of depth is not an absolute chemical boundary, but it does push a wreck into a colder, darker part of Lake Michigan where many deterioration drivers slow down. In cold freshwater, marine growth is limited compared with the ocean, and the best preservation often happens when a structure becomes quickly buried in fine sediment that reduces fresh oxygen exchange. Cold, low-salt Lake Michigan can preserve aluminum, though steel and damaged joints still corrode. Bureau number 36175 settled upright in the mud. Half a century later, sonar and diver surveys still found the fuselage standing. Rivets, stenciling, and geometry intact enough to confirm an SBD and make a museum recovery feasible. Preservation wasn't uniform. Steel parts and sediment-buried areas showed more corrosion than the aluminum skin. With identity confirmed, the mission flipped from search to extraction. The upright posture of the fuselage presented the best possible scenario for a museum recovery, but it simultaneously generated a severe mechanical hazard. The dive bomber had spent half a century settling deep into the cohesive mud of the lakebed. The internal structure was perfectly preserved chemically, but it remained structurally compromised by the violent crash dynamics that had previously torn away the engine and crushed the forward wing roots. The open, torn firewall represented a massive structural vulnerability. The recovery team faced a strict physical constraint. Any vertical lifting force applied to the airframe would first have to overcome the immense, clamping suction of the lakebed mud. Applying uncontrolled tension from the surface risked ripping the fragile, hollow fuselage apart at its pre-existing stress fractures. How do engineers break the suction of 50 years of mud without crushing a compromised fuselage? With the wreck verified, the question became mechanical. How to break decades of mud suction without ripping the fuselage apart? In 1994, the Navy brought in A&T Recovery to design that lift around Bureau number 36175. The deep lake conservation had preserved the external skin, but the internal structural integrity was fundamentally compromised. The original crash dynamics had torn away the heavy engine, leaving the forward firewall and wing roots severely weakened. They couldn't simply haul upward, the release had to be staged and gentle. To overcome this physical boundary, the recovery team used a staged lift designed to break the mud's grip without tearing the fuselage apart. Divers rigged broad lifting straps around strong points to spread the load, then added buoyant assistance so the airframe rose slowly and evenly. The goal was not brute force, but a controlled release that let suction give way without snapping the weakened structure. Once the suction was defeated and the airframe floated clear of the bottom, the extraction transitioned into the vertical hoist phase. The wreckage was carefully towed through the water column and aligned beneath a surface recovery barge. Here, the handling plan required transferring the suspended load from the buoyant lift bags to a rigid mechanical crane. To prevent the wings from folding upward under their own waterlogged weight during the transition into the air, the salvage crew utilized a spreader bar system. This rigid steel framework maintained a strict vertical alignment for the lifting straps, ensuring the load forces bypassed the compromised wing roots and pulled straight up from the attachment points. As the winch engaged, the Dauntless broke the surface of the lake. At this exact moment, the operational hazard shifted from structural tension to dynamic weight. An aircraft fuselage acts as a massive scoop, trapping tons of water and dense silt within its internal compartments. If hoisted too quickly, this trapped mass would instantly crush the lower fuselage structure. The crane operator was required to halt the upward lift precisely at the waterline. This deliberate pause allowed the massive volume of internal water to drain slowly through the pre-existing crash fractures and drainage ports, shedding thousands of pounds of sheer fluid weight before the airframe fully cleared the surface. Once it surfaced, oxygen and drying became the new enemy, so the crew kept it wet, rinsed away sediment with freshwater, and controlled drainage to prevent collapse. The United States Navy assumed official chain of custody of the secured airframe, recording the recovery as successful. The salvage engineers had safely decoupled a shattered machine from its hostile environment through strict geometric discipline. What happens to a perfectly preserved artifact when institutions prioritize combat history over physical integrity? A structurally preserved artifact, protected from the ravages of corrosion for half a century, was systematically dismantled by its own curators. Following its successful extraction from the freshwater lakebed, Bureau number 36175 entered a secure institutional supply chain. The United States Navy transferred the largely intact fuselage to the National Naval Aviation Museum in Pensacola, Florida. This transition marked a fundamental shift in the operational reality of the airframe. The threat of chemical degradation had been mitigated by rapid surface stabilization, but a new, strictly procedural hazard emerged. The museum complex housed an immense inventory of historic aircraft requiring constant maintenance, structural support, and authentic replacement parts. The highly intact Great Lakes artifact was immediately placed into long-term storage. For more than 2 decades, roughly a quarter century, the airframe remained out of public view, locked in a logistical holding pattern, while the museum evaluated its institutional value against the needs of the broader collection. The ultimate fate of this Dauntless was entirely dictated by the provenance of its operational history. In the strict hierarchy of aviation curation, combat pedigree supersedes structural integrity. Bureau number 36175 was physically pristine, but it had no combat pedigree, only a Lake Michigan training loss. The museum curators faced a harsh logistical trade-off. They possessed heavily degraded combat veteran aircraft that desperately required authentic structural components to remain viable for display. Fabricating the complex compound curves of a 1940s wing panel from modern aluminum is highly inefficient and strips the restoration of its historical authenticity. Simultaneously, the curators controlled a perfectly preserved but historically secondary training airframe. The institutional decision logic was clear. The structurally sound training aircraft would be utilized to ensure the survival of the combat veterans. So the Great Lakes airframe became a parts donor, artifact cannibalization in service of the combat veterans. Instead of restoring this specific SBD-5 to its original configuration, engineers treated it as a pristine parts donor. The airframe was subjected to a controlled structural reduction. Curators identified which components of the Great Lakes wreckage could directly replace the failing or missing sections of their primary exhibit aircraft. The incredibly rare state of preservation that made the initial recovery operation so successful now made the airframe an irresistible resource for spare parts. The disassembly process targeted the most robust and geometrically complex sections of the surviving structure. Engineers specifically targeted the outer wing panels. These massive aluminum assemblies had survived the initial water impact in the 50 years of submerged pressure, only to be unbolted and stripped from the central fuselage inside a climate-controlled hangar. Removing these panels was a precise mechanical operation. The wing attachment joints are high-stress structural nodes, and extracting the panels without cracking the vital aluminum required careful handling and specialized bracing. Once detached, the outer wing panels were separated from the primary structure and redirected within the wider restoration ecosystem. Critical internal components, brackets, and intact hydraulic reservoirs were also harvested to support other airframes in the collection. This post-recovery workflow represents a stark procedural reality. A structurally coherent machine, salvaged at immense expense and extreme physical risk, was legally and intentionally depleted by the exact institution tasked with its preservation. By the end of its 25 years in storage, as the footprint of Bureau number 36175 had been drastically reduced. The once complete survivor of the Great Lakes was now a hollowed core. Only the central firewall aft fuselage, the tail section, and the detached engine remained in the inventory. The pristine structural identity of the Dauntless had been irrevocably altered, not by the violence of its crash, but by the cold logic of museum supply chains. The airframe was no longer a complete aircraft. It was a depleted collection of surviving geometries waiting for a final logistical pivot. Can a scattered and depleted fuselage ever reclaim its structural identity? In early 2021, the operational trajectory of the depleted Great Lakes artifact shifted fundamentally. After years in storage, the surviving elements were finally transferred. The Military Aviation Museum acquired the remaining firewall aft fuselage and the complete tail section, initiating a highly complex rebuild program. This acquisition removed the Dauntless from its static storage environment and placed it into an active engineering pipeline. However, the machine that arrived at the facility was vastly different from the complete aircraft hoisted out of the lakebed decades earlier. The museum engineers immediately conducted a physical baseline assessment of the surviving structure. The prior artifact cannibalization phase had stripped the aircraft of its outer wing panels, hydraulic reservoirs, and critical internal brackets. What remained was the hollowed core of the fuselage. The heavy steel engine mount and the massive radial power plant were completely detached, carrying the permanent physical damage of the 1944 impact deceleration. Reconstructing this fragmented collection of parts into a structurally complete and potentially airworthy machine presented a severe logistical constraint. The required aluminum fabrication, complex riveting, and structural alignment exceeded the capacity of a single traditional restoration hangar. To bypass this bottleneck, the project directors initiated a distributed modular restoration. This is the modern forensic restoration strategy of separating an airframe into physical zones, such as the fuselage core and the outer wing panels, and shipping them to different global facilities that specialize in those specific structural geometries. Because different sections of an aircraft require completely different fabrication jigs and engineering tolerances, dividing the labor ensures maximum precision. The strategy effectively splits the engineering workflow across multiple continents to mitigate local facility limits. Then the hardware started moving. The original center section, the surviving tail structure, and the crushed forward firewall were loaded into standard shipping containers and transported across the Pacific Ocean to a highly specialized contractor in New Zealand. This facility was tasked with the primary fuselage reconstruction. Their objective was to mathematically realign the central structure, repair the torn forward bulkheads, and fabricate a new heavy steel engine mount capable of supporting the massive weight of a radial engine. They had to mate new aviation-grade aluminum directly to the 70-year-old metal that had survived the deep freshwater lakebed. Simultaneously, the missing outer wing panels presented an entirely different fabrication hazard. To solve this, the museum routed the wing reconstruction to a separate specialized facility located in California. The engineers there were required to rebuild the massive wing structures from scratch, incorporating the highly complex perforated dive brakes that define the Dauntless operational profile. Forming the compound curves of the wing leading edges demanded specialized presses, jigs, and custom bucks, built to match original Douglas geometry from 1943. The ultimate hazard of a distributed modular restoration is the final physical integration. The structural tolerances of a heavy dive bomber are measured in fractions of an inch. The wing attachment nodes fabricated in California must perfectly align with the center section shear webs rebuilt in New Zealand. If those bolt holes drift even slightly out of alignment, the heavy steel shear pins will fight the fit, and the massive flight loads cannot be safely carried through the airframe. The project managers must force absolute dimensional control across a global supply chain to ensure the separated zones form a single, rigid load path once they are finally joined. This modern rebuild strategy permanently alters the legacy of Bureau No. 36175. It is no longer just a preserved training wreck or a hollowed parts donor. Reassembling the scattered geometries into a single coherent machine requires strict evidence discipline and uncompromising engineering standards. When the complete airframe is eventually mated together, it will encapsulate 3 distinct operational phases within its aluminum skin. It carries the physical deformation of the training failure over the Great Lakes. It holds the pristine structural core preserved by half a century in an anoxic thermal layer. Finally, it stands as a measurable baseline for modern forensic recovery, proving that a depleted artifact can be systematically engineered back into a complete operational geometry.